Michio Kaku, a renowned physicist who has made significant contributions to material science, recently confirmed that the James Webb Space Telescope, JWST, has found 6 massive galaxies that scientists had previously believed were impossible to exist. These discoveries, which cast doubt on accepted notions on the origin and evolution of galaxies, have the power to fundamentally alter our knowledge of the cosmos. Given that Kaku is a well-respected member of the scientific community and has expressed openness to the remarkable outcomes of the JWST mission, it is clear that these discoveries are significant. In contrast to certain scientists who exhibit greater skepticism, Kaku accepts these discoveries, indicating his dedication to deepening our understanding of the universe. Kaku admits that the JWST's discoveries have piqued his interest, and his tone is brimming with excitement about them. While Newton's laws and Einstein's theories of relativity are fundamental, Kaku has demonstrated throughout his career that he is open to considering new theories and that they do not fully capture the complexity of the cosmos. While many of his contemporaries are still reluctant to embrace this idea, he acknowledges that the JWST's discoveries have the potential to advance science. Proponents of the Big Bang Theory and opponents of quantum mechanics have expressed concern over this skepticism, but Kaku is unfazed, pointing out that the JWST has discovered galaxies that date back to the earliest periods of the universe, each with more stars than our Milky Way, despite the fact that they formed only 200 to 700 million years after the Big Bang. These remarkable galaxies have been termed universe breakers by the scientists who produced these groundbreaking discoveries because, if verified, they would drastically change our comprehension of the cosmos. The conventional wisdom that galaxies developed gradually over billions of years appears to be challenged by these findings, which indicate that the early cosmos was significantly more dynamic and complicated than previously thought. This finding begs important concerns regarding the age of the universe, which was previously thought to be far older, and whether complex cosmic structures formed earlier than thought. These concepts run counter to conventional scientific wisdom, which frequently finds it difficult to explain these unexpected discoveries, and some physicists doubt the accuracy of the age determinations for these galaxies. Kaku presents a critical viewpoint, pointing out that the fame of some scholars have helped to keep many out-of-date and false hypotheses alive. He thinks that the flaws in these well-established theories are frequently revealed by a crucial experiment. This statement emphasizes how crucial experimenters are to the scientific method, which mostly depends on ongoing validation and improvement. According to Kaku, we hardly comprehend the universe's original origins on Earth, underscoring the need for rigorous investigation and a re-evaluation of accepted hypotheses. According to the Big Bang hypothesis, which was developed in 1927, the universe started as a single point and has been expanding ever since. The idea of a universe with a beginning and an end was not easily understood at the time by either the general public or scientists. Scientists are still having difficulty understanding these complexity today. The results of the JWST are at odds with the long-standing scientific consensus about the Big Bang idea. Still, the past has demonstrated that science is best when it is re-examined and kept open to novel concepts. For instance, when Einstein was a young boy, it was thought that the planets and stars were fixed in place and occupied particular regions in the universe. We now understand that everything in the universe is in motion, ranging from enormous galaxies speeding across space to planets orbiting stars. This growing body of knowledge forces scientists to face hard facts, realizing that theories are only theories until they are rigorously tested and closely observed. The observation that galaxies are separating from one another, a process explained by Hubble's law, which implies that the universe is expanding, led to the theory of the Big Bang. This concept seems to be supported by a number of factors, such as cosmic background radiation and the redshift of light from distant galaxies. But it's important to keep in mind that those who held geocentrism and the flat Earth theories in the past had their own kinds of proof for their beliefs. This predicament is similar to the current state of cosmology, where scientists were expecting the JWST to validate current Big Bang theories, but instead found 6 utterly inconceivable galaxies. This circumstance serves as a reminder that science is a dynamic field and that scientists need to be open to new findings and constantly re-evaluate their theories in light of the available data. The surprising results have forced certain long-held cosmological theories to be re-examined. Redshift is one of the most important tools used by scientists to determine measurements in the study of the universe. The term redshift, also known as the Doppler effect, describes how the color of light changes as an observer and the light source move in relation to one another. An automobile, for example, makes a louder sound as it gets closer and a quieter sound as it gets further away. Similar to this, the light from a far-off star changes to bluer wavelengths as it approaches us and to redder wavelengths as it travels away. For measurement purposes in their studies of the universe, physicists translate redshift values into speeds and distances. Small inaccuracies in these measures, however, could have a big impact on interpretations, therefore existing approaches are being closely examined. It will be interesting to observe what conclusions scientists draw from the most recent discoveries about our universe. It is imperative to examine whether the results are indeed the result of redshift errors, or whether certain researchers are only disputing the facts. This calls for a detailed examination of the data and research methods, as well as a thorough study. The constant review and evaluation of measurement techniques is a prime example of how scientific research is always changing. We appreciate you watching this video, and we will now end. Please feel free to ask questions in the comments section. If you found the information interesting, please subscribe to the channel for more insights, hit the like button, and share it to reach a wider audience. A community of inquisitive minds ready to investigate and comprehend the most recent scientific discoveries is fostered by this call to action. With its enormous breadth and intricate celestial bodies, the study of our universe still fascinates and challenges scientists all across the world. Every new discovery, from the most recent ones made possible by cutting-edge technology to the first theories about the universe, changes our perception and expands the body of knowledge. The genesis and evolution of galaxies, vast cities of stars, gas, dust, and dark matter held together by gravity, remain one of cosmology's most persistent mysteries. Comprehending the formation and evolution of galaxies is essential to solving cosmic riddles and validating or refuting established hypotheses, including the Big Bang theory put forward almost a century ago. Some of the basic tenets of the Big Bang hypothesis have been called into question by recent discoveries, particularly those made by the JWST. Due to the exceptional sensitivity and resolution of the JWST, galaxies that date back to a few 100 million years after the Big Bang and appear surprisingly large and luminous have been found, defying conventional understanding and pointing to a more dynamic early cosmos than previously thought. The consequences of these findings are significant, forcing scientists to reconsider their current models and posing queries regarding the mechanisms and timescale of galaxy formation. The idea that cosmic growth happened gradually over billions of years is called into question by the discovery of extremely advanced galaxies soon after the Big Bang. The JWST's observations shed light on the intricacy of cosmic history by showing how quickly galaxies can develop and go through periods of tremendous star formation early in their histories. These discoveries compel astronomers to revise their hypotheses regarding the formation of the first galaxies through the interaction of stars, gas, and dark matter in the early universe. These findings not only complicate our knowledge of galaxy formation, but also highlight how important technology advancements are to expanding the boundaries of astronomical inquiry. Scientists may now look farther into space and further back in time than ever before because of the JWST's infrared capabilities. Astronomers can recreate the histories of distant galaxies and learn more about the conditions that prevailed during the early stages of the universe by examining the light that these galaxies emit. One important technique in cosmological research is redshift, which is used extensively in these investigations. The term cosmological redshift refers to this phenomena, which gives important details regarding the speed and distance of an object from Earth. Scientists may determine the size, age, and evolutionary stage of galaxies spotted by observatories such as the JWST by carefully examining redshift data. But deciphering redshift measurements necessitates accurate calibration and knowledge of possible error causes, including instrumental constraints and gravitational lensing. Larger cosmic formations like galaxy clusters and superclusters, which provide insights into the distribution of matter on cosmic scales, are being studied by astronomers in addition to individual galaxies. Researchers are able to follow the cosmic web, a massive structure that spans the cosmos and specifies the large-scale organization of galaxies, by mapping the spatial arrangement of galaxies and calculating their velocities. Cosmologists also rely on the cosmic microwave background, CMB, radiation as a vital source of information. The CMB is the faint glow of radiation left behind from the Big Bang, which was unintentionally discovered in 1964. This unavoidable background radiation was left behind as the early universe's extreme heat dropped to just a few degrees above absolute zero as it expanded and cooled. Extensive observations of the CMB's temperature variations offer a glimpse into the early phases of the universe, exposing variations in primordial density that eventually gave rise to the big structures and galaxies that we see today. The CMB has been mapped very well by satellite missions, such as the Planck Observatory, confirming important Big Bang Theory predictions and exposing anomalies that defy existing cosmological explanations. The existence of cold spots and abnormally big holes in CMB maps is one example of an anomaly that points to unanticipated patterns in the density distribution of the early cosmos. Cosmologists have disagreed over these anomalies, leading to the development of alternative theories including inflationary cosmology, which holds that the universe experienced a brief period of extremely fast expansion in its early history. The search for the primordial principles of cosmic architecture goes beyond conventional astrophysics techniques. In order to investigate fundamental particles and forces, particle physics, particularly studies carried out at high-energy colliders such as the Large Hadron Collider, LHC, aims to replicate the harsh circumstances of the early universe. The two foundations of current physics, gravity and quantum mechanics, may be reconciled through theoretical frameworks like quantum gravity and string theory. These grandiose ideas seek to reconcile contradictions between Einstein's general relativity and quantum field theory by unifying our understanding of the universe at its most fundamental level. In a similar vein, the hunt for dark energy and matter still fascinates cosmologists. Dark matter, which is thought to make up around 27% of the universe's total mass energy content, is invisible to the naked eye but has a gravitational pull on galaxies and other cosmic structures. Due to its elusiveness, many theoretical and observational attempts have been made to determine its constituent particles and comprehend its function in cosmic dynamics. Similarly, the accelerated expansion of the cosmos seen in recent decades is powered by dark energy, which makes up around 68% of the universe's energy density. Its features and origin are yet unknown, raising important issues concerning the nature of the fundamental forces guiding cosmic evolution and the eventual fate of the universe. Interdisciplinary cooperation and the integration of observational, theoretical, and experimental methodologies are necessary for the investigation of these central topics. Together, cosmologists, particle physicists, astronomers, and astrophysicists are attempting to decipher the enormous code encoded in the universe's structure and light. In summary, our exploration of the universe is a voyage of learning and reflection, demonstrating the inquisitiveness and inventiveness of the human race. Every generation of scientists, from the first cosmologists to those studying the cosmos through space telescopes, contributes fresh chapters to the tale of the universe. With every new discovery we make about galaxies, dark matter, and the cosmic microwave background, our awareness of our location in the vast universe grows.